Well, looks like you are, because now it's got
Oh,
it changed the signal to stop recording. So yes.
right, right. Now, on the previous webinar that we did you get a recording of that? Because I don't remember doing
I
that.
did.
Okay. Would you have an edited link for that one that you could send to us?
Sure.
Yeah, because I don't, if you sent it to me, I missed it. Welcome to anyone that's joined us a little early. We'll start this webinar on the hour here in just a few minutes. Appreciate you joining us. Yeah, again, welcome to anyone that's joined us early for this head pressure control webinar, which will start on the hour in just a couple minutes. Again, welcome to all of you who've joined us for this webinar. We're getting ready to start here in just a minute or two. Hope everyone's having a good day. I'm Jim Jansen. I got Jason Forshee with me here from Sporland.
Hello, everybody.
Jason's just telling me he's running out of good weather to drive his fancy old Ford to work because it's fixing to get bad weather around here.
You know, it's starting to temperature drop off and my heater doesn't work too well.
Looks like we're on the hour. And Don, if you're out there, looks like we've got this thing recording. Hopefully we're showing a screen and we're ready to start.
It looks good to
So-
me, Jim. Thank you to both of you for putting this webinar on.
Don, you're most welcome. Most welcome. We're glad to do it. We're glad to do it. So we'll get started. The way this works is that you can enter questions into the chat. We'll tend to those towards the end of the webinar and try to answer all the questions you pose to us, at least the ones we can answer. Right, Jason?
That's right.
So it's showtime. Thank you for joining our webinar on single and dual valve methods for head pressure control. We'll discuss the operation of both methods and how they can be used to control high side pressure and keep the vapor compression refrigeration system running all year round. Thanks to Heatcraft and Mr. Don Fort for inviting Sporland to participate in this program. We're really glad to help you. Here's a bit of a shameless promotion for an additional webinar that we've been asked to present. And that's if Don will let us come back. On December the 14th, we'll take you inside the thermostatic expansion valve, or TXV if you prefer that moniker, the TEVs that get used in refrigeration applications. We hope you'll join us then. Hello, I'm Jim Jansen, Senior Application Engineer for Sporland. That's me on the left here. I've been with Sporland for almost longer than I care to admit, and I've done a lot of different jobs along the way. And joining me today is Jason Forshee over here. Jason's an application engineer on the Sporland technical support team. Jason's got a lot of experience with us, both as a design engineer and as a product manager. And he's served as a key developer for Sporland's virtual engineering selection software program, if any of you have used that. And he's currently managing the development project for that software package. And I'm really glad to have him along today.
Glad to be here.
You should just say hi.
Hi.
If you've got follow-up questions at the end, you can put them in the chat and we'll do our best to answer them. And by the way, we have a tech support team that will help you on all Sporland products. svdtechsupport@parker.com is the email address, or you can always call area code 636-239-1111, and you can find your way, navigate yourself to tech support, and we've got people like Jason here that'll help answer questions for you. Here's the basic vapor compression refrigeration cycle. And it includes 4 primary components that you can see highlighted here. It includes the compressor, which does its job to create the high and low side pressures in the system. There's a condenser, which rejects the heat to the ambient that's collected from the space that you're trying to cool. You've got a metering device. In this particular diagram, we've got a thermostatic expansion valve. And then, of course, you have the low side heat exchanger, the evaporator, which is absorbing the heat from the refrigerated space. And it's a heat transfer effect that's going on here, which creates the cooling or the freezing or the chilling or whatever you're planning to do with it. That modern refrigeration system can be pretty advanced and seem very complicated. Jason, have you seen this rack before?
That looks like the rack that's out in our lab.
Yeah. Some installations have multiple distributed racks throughout the store if it's a supermarket. Other designs include 1 or more compressor racks in a mechanical room with split suctions intended to satisfy both low and medium temp refrigerated cases. These systems may include different refrigerants, condenser types, unloaders on compressors, subcoolers, heat reclaim, head pressure control. And here you can see a bank of compressors, control panels, an oil separator over here, an oil reservoir, oil filter, oil level controls, and even examples of our Y1236 differential valve.
Gotta kind of squint to see those.
You kind of do, but they're there.
They are.
And here is that type of system in a schematic form. And again, it can seem quite overwhelming, but if you remember, you got four main components, no matter how complicated the system. And if you look at it from that standpoint, it's not that complicated. And today we're going to talk about this part of the system on the high side. And there's three factors that really affect the capacity of a condenser. And we've got an air-cooled condenser depicted right here. And they are, tell us about temperature difference there, if you can untie your tongue.
Yeah,
Jason.
I know. Sorry about that. The difference between the TD is the difference between the air temperature and the refrigerant temperature, and the condenser capacity increases with TD. So TD increases as the ambient falls.
And you have to forgive Jason. He's not used to talking to people.
No.
And he's got to talk to me right now. And I guess I'm not really considered a people.
No.
But as that ambient temperature drops, less heat may need to be rejected through the condenser. And this will likely cause the high side pressure to fall or drop with it. And so further actions needed to prevent the high side pressure from falling below a design parameter. Tell us about airflow there, Jason.
So VFDs are variable frequency drives, and fan cycle switches are used to decrease the airflow and optimize condenser efficiency. As ambient temperature falls, less heat may need to be rejected through the condenser.
In the old days, that might have been a 2-speed motor, but with the advent of inverter drives or variable frequency drives, that's made it even more sophisticated. And then coil size comes into play, and we can do fancy things like split condensers and add holdback valves to help control the pressure. And typical design sequences will cycle fans to modulate the air side, modulate fan speed. Like I said, we can split condensers, or perhaps even include a combination of all of these options in order to maintain condenser pressure, because that's important. And as we go through this, we're going to tell you why that's so very important. Keep in mind, at low ambient temperatures, fan control alone may not adequately control condenser or head pressure. And refrigerant side controls by way of a holdback or bypass valves generally becomes necessary at lower ambient temperatures. Lower ambient temperatures in the range of probably, as you can see here in the fine print, somewhere in the 50 Fahrenheit to 55 is where that comes into play. Now, there are typically a variety of controls on the high side of the system. And we have different presentations where we address the use of a heat reclaim valve to make use of that rejected heat so it's not just going to waste. And there are techniques where you split the condensers, as you can see being done here, so that you can minimize the surface area of the heat transfer surface at times where you don't need all of it. And then there are head pressure controls, which we're going to focus mostly on that during the course of this presentation. System condensing pressure, or head pressure, is directly related to that ambient temperature that we talked about. And as the ambient temperature falls, so will the head pressure in the system. At a certain point, head pressure will eventually approach suction pressure. Now, if you reduce the pressure drop that's available across the thermostatic expansion valve, if that's what you're using as a metering device, you can get to a point where it'll no longer feed refrigerant.
About 50 PSI or so.
A differential of that, is that where that happens?
Yeah.
Now, if you get to that point, the case temperature is going to suffer, meaning the temperature will likely increase. And that's not good for the product that you're intending to cool or freeze. Scroll compressors, for instance, need a minimum pressure differential to maintain engagement of the scroll sets. And low differential pressures across reciprocating compressors can damage reed valves due to those low flow rates and density issues. Sounds like something that's worthwhile to look into. Mm-hmm. Now, head pressure controls, like we've said, can include a combination of air side control, which can be cycling fans, modulating fan speed, 2-speed motors in the old days, variable frequency drive.
And now you're acting like me.
You're rubbing off on me. There's even louvers and dampers that get deployed, but that can ice over in the winter. Then you move over into refrigerant side controls, which effectively are used to flood refrigerant into the condenser. And we'll talk more about that here in just a minute. And remember this, as the ambient temperature falls, so will the head pressure. And to maintain the flow of refrigerant and protect the compressor, the condenser and liquid pressure must remain near those original design conditions. Now here's something that we just wanted to show to you that's more of a split condenser technique. And this is an example. It shows a split condenser and some of the required controls. Typically, you'd see a split condenser valve here, which is a fancy solenoid valve. And we've got a complete presentation that discusses that practice. We've included this diagram here because sometimes we get questions about this particular technique that's used in some applications. Some supermarkets prefer to use two normally open solenoid valves in lieu of that traditional three-way split condenser valve here. Flow is always present through the summer-winter condenser section, and a solenoid coil is not needed on this normally open valve. It is present simply to balance flow and pressure drop.
Right.
And we oftentimes get questions. There's two solenoid valves here. Only one of them has a coil and the other one doesn't. Why are you doing that? And that's why that's getting done. So we just thought, because of this rather interesting technique, we thought it was worthwhile to show. And now we're going to get back to head pressure control. Here's a simple schematic. This is one example of a two-valve version of head pressure control. The neat thing about it, as you'll see as we go along, it is an adjustable combination. You see one valve here and another valve here, which just almost looks like a copper or brass fitting, but is actually a valve. You'd use a combination like this on something like a walk-in cooler or a remote condensing unit. The ORI, or open on horizon inlet, is in this drop leg, and it responds to pressure at the outlet of the condenser. It opens on a rise of inlet conditions. This other valve over here opens on a rise of differential. And it backs up refrigerant into the condenser while increasing the condenser pressure. That's what this valve is doing. And the ORD helps keep the receiver over here pressurized. We're going to do, yes.
So
Something that's worth noting, you're going to point it out. Go ahead, tell me.
that the ORI valve is not compatible with 410A or CO2. And then the ORD valve will work for 410A if you're using a CDS valve or an electronic valve for the condenser holdback valve.
And you're jumping ahead.
I am jumping ahead.
Yeah.
I'm sorry.
Yeah, but we got a whole bunch of stuff we're going to talk about in between now and then.
Okay.
But we're going to get to it.
We'll get there.
Yeah. And here's a little more detail on what's going on. We're maintaining condenser pressure by flooding the condenser during low ambient operation. Pretty neat.
Yeah.
This valve helps that to happen. And we got a nice cutaway here of this ORI-T version. And it has an adjustment mechanism that is located directly opposite. Here's the adjustment mechanism, directly opposite of the valve feature that is being influenced. In this case, the inlet. It opens on a rise of inlet pressure, so it backs refrigerant up into the condenser. It has a bellows in here, which you can see right there, which is a flexible seal, and it's that flexible seal that has a problem with
leaking.
if it is overpressurized, like in the case of
CO2
or 410A.
It'll pop right out.
Yeah, so it's susceptible to failure. There's also, it's a low temperature solder joint in the valve. What that means simply is don't overheat it when you're installing this valve. That's why we've got extended sweat fittings built into it to help keep you from doing that. If there is a leaking bellows, it can in fact impact the valve setting, and it might go unnoticed for years. Here's another good cutaway of both the ORI and the ORD. This is the differential valve. Something to keep in mind, we're talking about pressure regulating valves here. may either control inlet pressure, outlet pressure, or differential, not a combination of one. And it's not practical to think that you can install these valves in reverse and get them to serve some other function.
It's just not going to work.
It doesn't work. So this is a good cutaway of both of these valves at this point. Now, here is the open on rise differential. And in fact, this ORD is included as part of the OROA, which we'll talk about here in just a minute. But I thought I would share with you a little bit about how this particular valve functions as the pressure across it changes. If there's literally no pressure differential across this assembly, that valve remains.
Then it's going to stay closed.
It's closed. If we get up to the point where we got a 6 PSI differential across it, there's a friction sleeve in here that helps keep it from chattering.
Yeah.
And it's going to still be effectively closed. As you approach 14 PSID,
it's going to start opening up. It'll be cracked open a little bit.
and then at 20 PSI.
That is 20 PSI is going to be full open. It's our rated position.
And have you taken that into account in your selection program? How does that do that?
So virtual engineer will take into account the stroke of the ORD based on the system pressure and rate it accordingly.
That's pretty neat. This shows that we've got different versions available depending upon the natural pressure drop that you're going to see in the system. And we've got different spring strengths in these different products. Now, here is an example of a single valve head pressure control mechanism. It's the OROA. It combines the function of the ORI and the ORD. Again, you would use this when only one valve was desired to be utilized in the system. And keep in mind, something you might know, originally this was sold as 2 valves. It'll make more sense when I pull up the next diagram. It responds primarily to outlet or receiver pressure. So it opens on a rise of outlet. There's 3 connections that you have to make in the system to install this valve, and it is non-adjustable, which means we build this valve to a particular setting. Standard charged to as a setting would have pressures of anywhere from 100 to 180 to 210 PSIG. We've done custom settings for OEMs when they've requested it in the past. And again, Jason?
Not suitable for 14A or CO2.
Now, here's a nice cutaway of that product. Here you can see, if you look closely, this is the ORD.
Mm-hmm.
And at one time, when you bought this valve, you bought an ORO and an ORD, and you had to braze them together out in the field. And this was our first, or one of our first value-added assemblies that we offered to our customer base. And these 3 connections are tied to the discharge, the condenser, and then the receiver. Now here's another 1 valve option that can be deployed for head pressure control. Again, it's not adjustable. It's again charged to a setting with common settings of 100, 180, and 210. It's a 3-way valve. We make it in several different sizes, an LAC4, an LAC5, and an LAC10. The LAC stands for low ambient control. The LAC4 responds to discharge pressure. Discharge pressure bleeds around the push rod to the underside of the diaphragm, and this discharge pressure opposes the dome pressure. That's the stuff that we use to charge it to a setting. When the outdoor ambient falls, the condensing pressure falls, and when the discharge pressure falls below the valve setting, the dome pressure, the seat moves away from the discharge port and allows discharge gas to bypass the condenser. In the summer, you got full liquid flow from the condenser to the receiver.
Right.
The LAC 5 and 10 are built internally slightly differently. They respond to receiver pressure. When the receiver pressure drops below the valve setting, the seat moves away from the discharge port and allows discharge gas to bypass the condenser. And during cold ambient temperatures and system offline, discharge and our receiver pressure may fall below the set point of the valve. This causes the seat assembly to modulate, providing a passageway for refrigerant to migrate into the discharge line or the condenser. For this reason, we suggest the installation of a check valve in the drop leg between the LAC and the receiver. You don't need that on those two other versions that we have, like the OROA or the ORI and the ORD function nicely without that. Now, here, we've got a high pressure version of this product that is suitable for use on
410A, but not CO2.
but not CO2. Here are a couple troubleshooting tips for the OROA and the LAC. Let's say there's no refrigerant being fed to the TVs. What's a possible cause for that? Well, might actually have a low system charge, or a valve that's not functioning properly because it's lost its charge. Is that a possibility?
That's possible.
Yeah. If you have high condenser pressure, you might have an undersized receiver during the summer. In fact, there's been times where I know you've probably taken calls and you've done some troubleshooting, and one of the things you've learned is that
There's no receiver in there.
there may not be a receiver at all.
Some people,
They don't understand that.
yeah,
That's the key thing. If you're going to do valve side refrigerant head pressure control,
you need a receiver.
a dirty condenser or a blocked condenser with no airflow, possible cracked diaphragm, you'd have to replace the valve.
Here's some additional detail in the form of a cutaway for the various LACs. It's worth noting that many folks in the industry refer to the head pressure control valve as a headmaster. The term headmaster was originally an Alco product with a patent designed by a guy the name of Bassler.
Yeah,
Bassler?
smart engineer over at
Yeah.
Alco. I think he's long retired by now.
Yeah. And then Sportland's LAC product line is very similar to the old Alco headmaster valve, and it was introduced into the market when the Alco's patent ran its course. Just thought that might be something interesting.
Yeah, I mean, most everybody calls head pressure control headmasters, and inclusively across the board. And it's just that headmaster, we really had a home for the name.
Yeah.
Here's some more troubleshooting tips. Jason, why don't you tell us about this?
So if the valve is constantly bypasses discharge gas, that could be that the natural pressure drop exceeds the OROA's capability. So if there's more pressure drop between the condenser and the receiver than there is across the discharge connection,
You may need a different size
you need a different
with a
setting
different
for an
setting.
OROA.
Different setting.
And that's what that maximum pressure drop column is talking about there. Also, that if there's debris in the system, then that gets clogged in the port and the valve can't close correctly. So since it won't be able to shut off that discharge connection because there's some crud there. And then if the valve's overheated, all sorts of strange things can happen. So we really recommend that you keep the valve cool while you're brazing it in.
And this shows that depending on the pressure drop between the compressor and the receiver, we've got valves with different spring ratings built into them, both for the OROA and the ORD.
Yeah. Another question I get a lot on the phones is somebody will say, hey, I have a contractor came in here with an OROA-B. Can I just give them an OROA? Well, no, because then you're going to be bypassing the wrong spot.
That's a good point. There is some degree of simplicity with respect to the nomenclature for these products. And we've discussed this briefly already, but in the case of the ORI, its acronym here infers what it does. It opens on a rise of inlet. And the next placeholder in the nomenclature is port size in 1/8 of an inch. We make two sizes of this particular valve, a 6 and a 10. And then this is the nominal adjustment range, 65 to 225 PSIG. And then connections in the next placeholder. The versions that we sell through the aftermarket are most often equipped with an optional inlet strainer.
Yeah.
And then depending upon the application here, we've got the high pressure bellows built into it.
Correct.
The ORD, its name infers what it does as well. It opens on a rise of differential pressure. Now, in this particular case,
That's it.
we only make one size,
Right.
which I'm going to elaborate on that shortly, but that's always perplexed me just somewhat. And then this is the opening pressure differential, but we've stepped through the sequence of what it takes to get it to full rating. You can find lots of details about these products in our bulletin 90-30, which is free for you to download from sporlan.com.
Correct.
Here's some more nomenclature. Let's take a look at it for the OROA. The OROA is a non-adjustable single valve answer to the question of handling head pressure control. It opens on a rise of outlet. The initial A here stands for assembly. It's a port size in 1/8 of an inch.
Also only available in one size.
Only one size. Pressure setting, it's charged to a setting. We do have a variety of connection sizes, and then it has an optional strainer that gets the hammer handles and the lunch boxes. And then the LAC product line, low ambient control, both in 4, 5, and 10, which we don't have the 10 displayed here. We do have a dual setting version, and this one has a range associated with it if you incorporate that dual setting option. And then fitting combination, because we've got 3 connections to make, and then different styles of fittings, like this is the outside diameter female. Here's yet another 2-valve answer to the question of how to control head pressure. And generally, if the desire is to have the ability to adjust these valves, the 2-valve approach is going to be our best answer to that.
Right.
If you want to simplify the number of connections, if you want to simplify the number of products that you're using to control head pressure, then you can do it with a single valve, either in the OROA or the LAC product lines. This depicts the refrigerating specialties answer to this. Refrigerating specialties is part of Sporlan and Parker, and they manufacture these industrial style valves. They're generally going to answer the capacity requirements of larger systems. Here you see the Flowcon A8 and A9 valves. They serve the same basic purpose as the ORI and ORD valves, but with higher available capacity ratings for those industrial applications. They maintain condenser and receiver pressure during cold weather operation. Like I said, they're adjustable, they are serviceable. The A8 is the holdback valve that you see here. The A9 helps to pressurize the receiver. We may not have really elaborated on this adequately enough, but as you hold refrigerant back into the condenser surface, if you do not bypass this condenser and pressurize the receiver, you'll eventually starve the metering device. And so that's the function of the A9 or the ORD, is to help keep that receiver pressurized.
Artificially raise the head pressure.
Yep. Now, in these types of applications, most systems will have a ball valve downstream of the A9 valve. And when adjusting the A9, you might want to close that ball valve and turn the A9 appropriately to get it adjusted with a manifold gauge set attached to the line between the A9 and the ball valve. The refrigerant pressure here could be reduced to suction pressure. The A9 can then be adjusted to raise the outlet pressure to the desired point. Once the valve's set, you remove the manifold gauge set and open the ball valve for normal operation. That's just one approach that you can take. And I probably haven't mentioned it. We weren't trying to elaborate fully on all the Flowcon products, the refrigerating specialty products here. We are planning a webinar where we're going to highlight those, because we got a full range of hot gas bypass, Somebody's knocking at the door, it sounds like, Jason.
Yeah.
Hot gas bypass, EPR, and even applications like this. Now, when you deploy valve side head pressure control on a system, there's extra refrigerant that needs to be stacked up in the condenser during the winter operation. And it has to go someplace in the summer, and that's where the receiver comes into play. If you were to install valve side head pressure control during the time of the year when you needed it, and you installed the extra refrigerant, you're all fine without that receiver. Then you get into the summer months and you got a problem.
You got too much refrigerant.
Yeah. Valve side head pressure control absolutely requires the use of a receiver, a properly sized receiver, for this to function year round without any special attention. Now, the extra refrigerant charge and the receiver size are both critical components. You can refer to our Sporlan Bulletin 9030-1 for detailed instructions on how to calculate that. And to determine the amount of this additional refrigerant, the condenser volume and the volume of the associated piping as well must be calculated. So we've got charts in that bulletin that can assist with that process. However, more and more, we're seeing microchannel condensers being deployed. I'm going to suggest that you take a slightly different approach to handle this. And if you plan to retrofit this, you might want to consult with the manufacturer because they might have worked all these details out for you already.
Save you some math.
Now, then based upon the minimum ambient temperature, the percentage of the condenser to be flooded can be determined. And if I recall, Jason, didn't you recently update all this
Yeah,
information?
back in March, I updated this bulletin to include a lot of the 407s like A, C, F, H. We have 513A in there. Tried to do the best look ahead that we could on what refrigerant landscape was going to look like and include those.
Good deal. Now, that additional refrigerant that must be added to the system is something of a drawback when you consider flooded head pressure control. This is an added cost to the supermarket or to the building owner, and the added refrigerant is at risk of being lost through any external system leaks. So combining more than one method of head pressure control, while it's common, you need to take into account that you need to have a good, clean, dry, and tight system. As Don would say, clean, dry, and tight. So if you got any leaks that you know that exist, you really need to go fix those leaks. And then at that point, it's time to replace the filter dryer and then add the charge till you have a clear sight glass or see-all, unless you know something different as far as what the manufacturer has recommended. And depending upon the ambient temperature, the valve side head pressure control, the OROA, as we're depicting here in this case, may be engaged and start stacking liquid up in the condenser. Again, you'd use Bulletin 90-30-1 to determine the amount of additional refrigerant charge needed for the system to operate at current ambient temps, and also determine the additional refrigerant for the coldest ambient temperature, unless the manufacturer has already done that for you. Make sure that receiver is large enough to hold the extra refrigerant. And here we're suggesting that once you've calculated that, you want to make sure that you don't go beyond maybe 80% of the limit of that receiver.
Right.
So make sure that that receiver is large enough to hold the additional refrigerant needed. Then you add that extra charge. In this diagram, we have depicted industrial style head pressure controls. Again, those Flowcon series A8 and A9. It's important to know that you can use those products to not only control head pressure control, but like I've said, hot gas bypass and EPR applications and others. And again, these valves are serviceable and adjustable. And they're just simply occupying the traditional locations of the ORI and the ORD. And it's not uncommon to combine both air side modulation with valve side refrigerant control to achieve the desired head pressure. You might have a sequence of events, something like this. As the ambient temperature falls, you could stage fans. If you had a bank of fans like it's depicted here, You could stage the fans to cycle off based on pressure and bring them on and off with respect to that. And then the fans would be staged ultimately to the final bank of 2 or maybe even down to 1 single fan that you might have fitted with a variable frequency drive. You could also split the condenser to minimize the surface area of the coil by deactivating the summer condenser only, and that's what we're showing here. You finish off staging the fans down to that final single fan, and in some instances, you might have all fans cycle to an off position before you start engaging the whole back valve and start flooding the condenser. You flood that remaining condenser to deactivate that coil with the A8 in this particular case. You can see here we got 165 PSIG rating or set point on this, and you maintain the receiver pressure and keep the metering device supplied refrigerant by use of this A9. Here we've got almost the same identical diagram, but we've substituted the ORD and the ORI for the A8 and the A9. These valves may simply have inadequate capacity for these large industrial systems, and that's when the A8 and the A9 would come into play. But we're illustrating it here just to show the functionality of these different combinations of valves. This shows the 2-valve approach, and the 2-valve approach would typically be used when you need to be able to adjust the valves. Now here's a neat little trick that not everybody knows about this. Like we've said, we only ever made 1 size of ORD, and we've shown the ORD4 here. And likewise, we only made 1 size of the OROA. We've made the OROA5. Again, that 4 is a relative term that indicates the diameter of the port in the ORD. Now, not saying that it can't be fitted with different springs to yield different settings, but for flow, we only have 1 show and 1 size, and that can be a limiting factor. However, like we've shown here, you could install multiple ORD4s in parallel to increase flow. In general, Sporlan head pressure control valves can be installed in parallel to provide higher refrigerant flow rates for large systems to satisfy load requirements greater than what any single valve's capacity could yield. I've seen systems with 2, 3, and even more ORD4s in parallel. Jason, what do you think that was indicating to us that maybe we should have?
Maybe we should have had a bigger size.
Yeah, no, maybe so.
Never did it.
We never did. Also, if a situation arises that's similar to what you were advocating earlier, if you need a higher setting and the required valve is not readily available, you can stack ORD4s in series as what we see here in the diagram. This could be used to prevent the system from bypassing the condenser at times when that wouldn't be desirable. The spring rating of the individual ORD4s would be additive, thus changing the set point. So 2 good things to know. While these techniques may best be applied to the ORD, in theory, they could be applied to other Sporlan PRVs as well. And Virtual Engineer coaches through how many will be needed for the application.
Right. If you're doing a larger application and you need more flow, it will tell you, hey, you need 2 ORDs for this application, or 3 or 4, or whatever that value is.
That's pretty neat. Now here's an example of an electrically actuated, electronically controlled valve being used for head pressure control. These valves can be used to control evaporator pressure, superheat, hot gas bypass, glycol flow in a secondary application, and even head pressure, as we're showing right here. You can see here we have a step motor valve in a place that would ordinarily have been occupied by an ORI. And we still are deploying an ORD over here to keep that receiver pressurized. There are specific standalone controllers available to tell these valves what to do to help complete the package for most applications. The step motor valve has the advantage of being less sensitive to the refrigerant installed in the system and can generally throttle down to lower levels as compared to their mechanical equivalent. Jason, what kind of levels can you achieve with that step motor valve?
You can get down to about 10% or so of its rated capacity.
Compared to what for the mechanical on average?
40,
30 to 40%?
yeah.
Now, here's one thing you can't do with a mechanical valve. You can monitor them remotely if the right controllers are in place on the job and you have it connected to the internet.
And you can just set it and you're done.
Now here, we've got a listing of a number of valves. You see here the CDS valve we've got set up to handle liquid hold or refrigerant holdback applications in the condenser. The CDS and the SDR could either one be used for receiver pressurization applications. So you could have step motor valves in both positions.
Mhm.
One as the holdback valve, one as the receiver pressurization valve.
Yep.
And again, then use the appropriate, in our case, Kelvin 2 pressure controller as a standalone controller that would be used to tell these valves what to do. Could also be used to communicate with the building automation energy management system and via Modbus, for instance. What's Modbus?
Modbus is a serial communication protocol developed by Modicon, I believe it was, for use in PLC controllers.
It's been around a long time.
It's been since the late 70s, early 80s, something like that.
And then we've got plenty of pressure transducers with different ranges available depending on the application. Something also, we can even support the conversion of certain mechanical valves, and we've got step motor actuators in kits that can be used to convert these products if you're doing a store remodel and that's important to you. We've seen energy savings realized in this kind of percentage in the 2% range with new store payback, half a year, less than half a year. Retrofit options, we got CDS kits available for instance, in this application in A8 with decent paybacks in that 1 year range. And I don't know, where did time go? It seemed like this went by fairly quickly and we're getting close to being finished. Don, if you're still out there, are we getting any questions?
We do have a handful of questions here.
We could start dealing with those now.
Shane's asking us, you keep saying that less heat needs to be rejected at low ambient. Shouldn't it be easier to reject that heat since it's low ambient?
Oh, it is. It makes that condenser ever more efficient, and that's what helps bring that pressure down.
Yeah. And then
what else you got there?
Yeah, I got another one. I got another one here from Frank. It says if debris gets in the valve, does it need to be replaced? And that's
well, maybe. It depends on the valve. Some of these valves, for instance, the ORI, the 6 and 10 have a fairly big port. You may be able to cycle the valve and break that debris loose, maybe.
Yeah, so with that, we'd recommend with an ORI 6 or 10, you would turn that adjustment stem all the way out, all the way back in, and let it, and see if that helps dislodge the debris. You'll have to watch the system for a little while. Sometimes that can work, not all the time.
With the CDS product line, you might be able to cycle that valve again, dislodge debris, depending on what it is.
The CDS, we have replacement motor kits also for the CDS, so you could
you could service it.
You could service that valve.
The A8 and the A9 refrigerating specialties valves could be rebuilt.
Yes.
Those are serviceable. I have seen things like pipe plugs in the inlet of a CDS valve, so you could cycle that all you wanted and you'd never dislodge that. You'd have to disconnect it from system piping to get things like that out. I've seen that in a new installation.
If you are going to open up a CDS valve, it'd be in your best interest to manually open that valve as far as possible.
How would you do that?
With like an SMA 12 standalone diagnostic device, or if the controller lets you have some sort of manual control over that valve. That way, when when you open that valve, it pulls the piston all the way in. And when you go to put the motor assembly back on, you don't have to worry about it interfering with the valve body.
Makes sense. More questions?
More questions? There was another one came in here from Steve. Can both of these valves be mounted in the vertical or horizontal position? I believe that question came in when we were talking about A8, A9 valves.
Oh, so it was focused on the refrigerating specialties products?
Yeah, if they can be vertical or horizontal.
That's a good question.
I think they can, but I'm not 100% sure.
Sounds like that's one of those questions where we need to confirm.
Yeah.
Vertical, horizontal. I know when we're talking about ORI, ORD, LAC, they are fairly compliant with however you need to mount them in order to fit them into the system. Step motor valves, you can get away with a lot of different orientations with that. The A8 and the A9, I am not 100%.
I don't think there is, but we'll have to look into that.
Don will get an answer for you and confirm that.
All right, please do. And if that individual can actually put their email contact information in the chat, that would be great, so we can close the loop on that question.
We'll do that. Yeah, if we'll look for that.
Let's see here. And then we have, as a presentation, going to be available on the Sporlan YouTube channel.
Well, I tell you what happens there. We're attempting to record this, and then Don Fort and Heatcraft edit this presentation, and then ultimately make it available to Sporlan. And when that happens, we'll go ahead and post that out on our YouTube channel, and so you could go back and watch this at your leisure.
Looks like we have some more requests for sending out.
It'll also be available on heatcraftrpd.com, our website, under training, and then videos. There's a host of videos there, and this will be yet another one that'll be available in that. After it's been distilled and freshened up, we'll certainly make that available there as well.
Yeah, they get all our tongue ties out of it.
No, it just makes it natural. Hey, no biggie, right?
Helps them know that we're human. And then we have another question here from David. Can you install an ORI without the ORD valve?
Well, you can.
You can do anything you want to do.
Yeah, but here's the thing. If you just and I'll back up here just a little bit, it might help to elaborate on this. But if you just back refrigerant up into the condenser, and I want to find an image of that here, come back here, I'll get the one I want. One more time here. If you just back refrigerant up into this condenser and you provide no means to bypass through this ORD into the receiver, you'll eventually starve this metering device, whether it's TV or not. So it's one of those things, if you're going to use an ORI, you really need to have this bypass leg built in with some type of differential valve built in there to have a little bit of control, so that it's just not freely bypassing all the time. Does that make sense? It does to me. If you're going to do the two valve control, you have one valve that backs refrigerant up into the condenser to help elevate the pressure. And then you've got a second valve here that keeps a steady stream of refrigerant supplied to the receiver so that you don't starve this rest of the system. Because if you simply back the refrigerant up in the condenser, you will elevate the pressure there, but it will be at the disadvantage of having the system continue to function.
Yeah, it'll eventually close off the condenser and you got no refrigerant.
You got more questions?
I have several more questions here.
Let's
We got Glenn saying, you mentioned fan cycling controls. Can you explain why valves might be a more reliable method of controlling head pressure?
Well, I think it's a double-edged sword approach. Fan cycling and staging fan motors or using variable frequency drive is a perfectly fine way to control head pressure, provided you're in the range where it functions well. And that is usually 50-degree ambience and above. I know there's places in South Florida and South Texas where they might have valve side head pressure control on their systems, but they don't come into play. It's when you get below those ambient conditions that the combination of the air side in conjunction with the valve side does a really fine job. And I guess that's how I would look at it. I don't know that you necessarily do one to the exclusion of the other, though there are systems that do.
Yeah, and at region specific, really. The more north you get, the more
the valve side really becomes an important component in the system, and it functions well in those colder climates. You know, if you're using things like dampers and motorized vanes, they might ice up.
Yeah.
And that becomes a problem, or the fans might ice up.
But if you live in a country, part of the country that never ices up,
or it never gets below 50 degrees Fahrenheit, then fan side is a reasonable approach. More question?
Let's see here. We have the smallest fitting size for the ORD. We have two options for you. We have 5/8 and 7/8.
There you go.
So the fittings on an ORD are 5/8 and 7/8 ODF.
Yeah, but one port size.
One port size. Yeah. And then the OROA has, this is from, if I try to pronounce this name, I'm going to butcher it. But the OROA has merged flow of the receiver pressurization in the condenser inlet. Will the differential affect when both flows open up? So how does that, when we're in the middle, somewhere in the middle of the ORA's control, when both flows are active, how does that work?
We got a cutaway here. So let's say that we're in a situation where we're in summer operation.
Yeah.
And the ORD portion of it is closed. So we've got flow from the condenser to the receiver. This seat disc here will open and allow flow to pass through this opening and onto the receiver. Now, as the winter months come into play, and this side has a differential applied to it, this will crack open and this will tend to go closed. And then there's a passageway from here that joins to here that will flow around this perimeter around this center tube, I guess is the best way to explain it.
Yeah.
And so they're not conflicting with one another, but you can have some flow from both sides and it modulates.
And it does modulate. And if you're operating really close to the setting of the valve, you might hear it chatter
or click. But this, you have closed passageways depending upon the time of the year, and hence no hard and fast need for a check valve here to prevent migration. More questions, Jason?
More questions. We have Lisa is asking what are our recommended settings for A8 and A9 valves.
Well, we had some options. It's going to kind of depend on the refrigerant in the system and the application, but we've got some suggestions here. Let's see, we've got 180 and 160 as a particular example. That's not hard and fast. It just depends on what refrigerant is in the system. Depending upon the refrigerant in the system, this number may need to go up or it may need to go down.
We typically like to see, try to size or put a setting for head pressure somewhere in between 90 and 100 degrees Fahrenheit. That way you know that your high side components are going to be sized correctly.
And again, we are planning a future presentation down the road to deal with the refrigerating specialties product line.
We have Steve was confirming that we were talking about the mounting orientation, the A8, A9.
And did you get an email address for
We
him?
do, and we have a couple other people that want that as well.
Okay, can you note those email addresses down?
Yes, I will take care of
You'll
that.
take care of that. Okay,
And
and then we'll confirm that. And I think what it amounts to is I'm reasonably sure, like we've depicted here, you can mount the valve with it pointing to the sky, and you can mount it in a horizontal position. What I'm not sure if you can point it to the ground. And that's what I need to confirm.
Okay.
All right, so what else you got?
We have, what is the recommended?
Oh, I'm sorry. Copy me on those replies too, if you would, please.
Oh, absolutely. That understood.
Okay.
We have, what is the recommended duration for service life? So for an ORI or an ORD or an LAC valve, how long can we expect those to stay in the system?
It's one of those things. If it's, and I like what I've heard Don say in the past. If it's clean, dry, and tight, and products haven't been overheated when they're installed, and they're working in nominal conditions, I mean, these valves can run the life of the system. So what does that mean? That's kind of it's one of those things it's tough to put a number to it. It's tough to make a guarantee, but it's almost as if they can run indefinitely. But that's a stretch. But what I'm suggesting is if it's clean, dry, and tight, nothing's been abused, nothing gets overheated, nothing's overcycled, these aren't things that you would normally necessarily have to go into
You can get many years of service life out of these valves if your system is clean, dry, and tight.
Yeah. Now, certain products, depending on how they're made, might be prone to leaks. And if you have leaks, or you've got to do preventive maintenance, that's one of those things you're going to have to address on an as-needed basis.
Okay, we have another one coming in here. Yes, makes sense. We have an ORA 5. Okay. This is a pretty direct question from Christine. If I have an ORA 5 100 on the low temperature 448A Larkin condensing unit, and the parts list shows a compressor discharge temp control valve, what would that valve be called? And I'm not exactly sure, because if you have an OROA 5 on there, you shouldn't need more than one head pressure control valve. And you might think about asking Larkin what they're referring to there. Because
No.
I'm not.
That's
That
fair enough.
raises my eyebrow a little bit, and I'm not quite sure
And
what they're doing.
they might have a specific schematic where they've detailed something in their plan of action that we don't know.
Yeah.
So I think that's a good approach. Maybe pose that question to the manufacturer.
We have a comment from Glenn that's saying that on a fan cycling system, that wind blowing, if you're in a high wind area, that can affect your fan cycling controls.
That's a good point.
That's a very good
That's
point.
absolutely true.
David is coming back to me and asking me when will the A8 valves be added to Virtual Engineer. So that kind of hits home.
And what is your plan with that?
So they're in there today for EPRs, evaporator pressure regulators. I do have a plan to get them in for head pressure control applications as well. I've been delayed on that, and I don't really have a good excuse other than it keeps getting falling off the radar.
You're lazy and slow.
I am lazy and slow, so it doesn't happen.
Yeah.
But we are adding a lot of things to Virtual Engineer. We keep adding stuff every day and tweaking things, and that one just hasn't made the end of the list of the day, but we do plan on getting that done, hopefully soon.
More questions?
More questions. We have more questions. Head pressure valves reduce the need for larger coil. Let's see. So Shane is making a comment here. Head pressure valves reduce the need for a larger coil and at low ambient temperatures. Christine's coming back and saying that, hey, her comment about the compressor discharge valve is Is it even part of the OROA operation? And it shouldn't be. So, but again, if they're doing something goofy there, I don't know what that is.
Well, it'd be kind there. We don't know the specific ramifications of the suggestion by this OEM. If you have a diagram that you could send to, say, Jason's email, he can take a look at the diagram or the specific instance and maybe comment on that.
Yeah, our email address and our technical support is svdtechsupport@parker.com. Hey, it's right there on the screen. Let's see here.
You got anything else?
Mind sharing the literature for this course, please. All of our literature is available on sporland.com. If you scroll about halfway down that site, there's a section that says literature, bulletins, and more. And then all the head pressure control stuff, after you click on that link, will be under 90-pressure regulating valves.
90/30, right?
Yeah, 90/30.
And it's free to download.
Yes.
And in fact, we've been talking about Virtual Engineer now for a while. That's our software program. That's, as long as you have an internet connection, that's free for you to use. And likewise, we've got a lot of technical support tools out on sporland.com, and all of it's free for you to utilize and deploy as you see fit. And again, you can call us anytime. 636-239-1111 will get you into our headquarters, and you can navigate over to tech support if you need help, and you'll catch guys like Jason and Kevin and Dennis and Steve, Pat, all who have considerable amount of experience, and we do that for free, and we'll try to help you.
And
what else you got there?
And then we have one more comment left in here from Steve, who's saying, going back to the A8, A9, saying he's mostly concerned about the valve pointing straight up in the air, so connections are left and right, and the valve pointing left to right, so connections are up and down. Not concerned with the valve being downward.
Okay, in those instances, I know we've seen those many times.
That's fine.
There's no ramifications against doing that.
And that is our last question in here. I did want to make one more comment, in that if you go on our sporland.com site, if somebody like myself or Steve is logged into our chat feature, you'll see a chat bubble there where you can talk to us that way as well. But obviously, I'm not monitoring that in the middle of the night. So,
well, but right.
But yeah,
but it is another avenue for you to get some
help,
assistance. Remember, we've got the webinar coming up in December. We hope you'll join us. Don, unless you've got something else to say, I'm going to tell you a big thanks, and thank you for inviting us to be part of your training program. We're delighted to do it. We hope we've been some help, and thank you for joining us.
All I have to say is bravo, gentlemen. Thank you for your time as well. I hope this was helpful to everybody online.
I hope so too.